On the last turn we were discussing about mixture of gases, and we learned that each constituent gas in a mixture of gases is assumed to behave like an ideal gas, and therefore the gas mixture is also presumed to obey all the laws of ideal gases. Then we discussed mass fraction of constituent gases. The mass fraction of constituent A is given by Ma by M. For gas B, it will be Mb by M, and so on. From the conservation of mass, we know that M is equal to Ma plus Mb plus Nc. By dividing by M, we have 1 is equal to Ma upon M, Mb upon M, Mc upon M, where these are the mass fractions represented by Xa, Xb and Xc, and we have seen that the sum of all the mass fractions in a mixture of gas is equal to unity or 1. Similarly, we discussed mole fraction of a constituent gas B, and that it is given by Mb upon M. If number of moles of mixture is given by M, N, it will be equal to Na plus Nb plus Nc, that is sum of the number of moles of all the constituent gases. By dividing by N, we have this expression which indicates that the sum of the mole fractions of all the gases is unity in a mixture of gas. And also on the last turn we discussed Dalton's law of partial pressures. First we discussed what is partial pressure, and then we derived this equation, that is P is equal to Pa plus Pb plus Pc. Now we proceed further and start with Amagat-Leduc law of partial volumes. The partial or reduced volume of a gas component represents the volume that this gas component would occupy if its temperature and pressure were equal to these parameters of the gas mixture. While discussing Dalton's law of partial pressures, we assume that each component of the gas mixture is filled in the same volume and at the same temperature, and then pressure was measured in each case, and it was assumed that Pa, Pb, Pc, etc. are the pressures in each case, and sum of those pressures was called the total pressure of the mixture of gases. If we keep the temperature and pressure same as that of gas mixture, then naturally the volume will reduce. That is, each component will occupy less volume than the volume occupied by the total gas mixture. So let us say, to maintain same temperature T and pressure P when the container is filled with gas A, the volume occupied by gas A to maintain same temperature and pressure is Va. Similarly, when gas B is filled in the container and same temperature and pressure is maintained, then let us say it occupies volume Vb. Similarly, in case of gas C, it occupies volume Vc. These volumes Va, Vb, Vc are called reduced volumes or partial volumes of gas components. Right? Now, ratio of the partial or reduced volume of each constituent gas to the total volume of gas mixture is called volume fraction. If the total volume occupied by the gas mixture maintaining temperature T and pressure P is V, then Va upon V will be the volume fraction of gas A, and it will be represented by Ra. Similarly, for gas B, Rb is equal to Vb upon V, Rc is equal to Vc upon C, and so on. Ra, Rb, Rc are volume fractions or reduced volumes of each constituent gas. Right? So this is what is Amagat-Leduc law says that the total volume of a mixture of ideal gases is equal to the sum of the partial or reduced volumes of constituent gases. How to derive this? You can see here. If P and T are the pressure and temperature of the gas mixture, then for gas mixture, the characteristic gas equation will be PV is equal to mRT. M can be replaced by N into M, where number of moles of gas mixture N, molecular mass of the gas mixture is M, then NMRT, and M into R, that is molecular mass into characteristic gas constant, can be replaced by universal gas constant, so it will be nR0T. And for the component gases, PVA is equal to NaR0T. P and T have been kept constant and reduced volume is Va. Number of moles of gas A are Na, so PVA is equal to NaR0T. Similarly for gas B, PVB is equal to NbR0T. PVC is equal to NCR0T for gas C. Now upon adding these components, PVA plus PVB plus PVC is equal to NaR0T plus NbR0T plus NCR0T. Right? So this is equal to, right hand side will be equal to nR0T, because sum of these number of moles is equal to the number of moles of the mixture of gases, nR0T. Now if you compare these two equations, V is equal to VA plus VB plus VC. So this is what is Avogadro-Leduc law of partial volumes. Right? Now divide this equation by V, it will give 1 is equal to V upon V, VB upon V, VC upon V, where V upon V is volume fraction of component A, VB upon V volume fraction of component B, and so on, RA plus RB plus RC. Right? So here again the sum of the volume fractions of constituent gases is always equal to 1 or unity. So when the analysis of a gas mixture is made on the volume basis, it is called volumetric analysis. Right? Now let us discuss relation between partial pressure ratio, mole fraction and volume fraction. The characteristic gas equation can be written as you have already studied, PV is equal to mRT is equal to nR0T for the gas mixture, and a general equation for constituent gases of the gas mixture, PIV is equal to MIRIT is equal to NIR0T, where I is indicating the gas constituent. For example, for constituent A, this equation will be PAV is equal to MARAT is equal to NAR0T. Similarly, for gas B, PBV is equal to MBRBT is equal to NBR0T. So here R0 is universal gas constant, T is temperature, V is volume, and remaining three are variables depending on the constituent gas. So from these two identities, you can, by dividing, obtain this, that is Pi upon P is equal to Ni upon N, or you can say Pa upon P is equal to Na upon N, Pb upon P is equal to Nb upon N. So what is this? Pi is partial pressure, this P is pressure of mixture, so Pi upon P is partial pressure ratio, and Ni upon is already, you have already studied, mole fraction. So partial pressure ratio is equal to mole fraction. Now if you consider the gas equation for reduced volumes of the gas, then it will be written like this: PVI is equal to MIRIT is equal to NIR0T. Here the variables are V and N, or V and M and R. Right? For gas A, it will be PVA is equal to NaR0T, PVB is equal to NBR0T, and so on. Now this is equation 4. Now if you see equation 4 and 1, you can say that Vi upon V, that is this equation divided by this equation, will be Vi upon V is equal to Ni upon N. Means volume fraction, because V upon V, Vb upon V, these are volume fractions. So volume fraction is equal to mole fraction. Now from these two equations, that is 3 and 5, you can say that Pi upon P is equal to Ni upon N is equal to Vi upon V. What does it mean? Partial pressure ratio is equal to mole fraction is equal to volume fraction. So in a mixture of ideal gases, the partial pressure ratio, mole fraction and volume fraction are all equal, right? Now the last equation suggests, if you remember the last equation, it says that Pi is proportional to Ni, that is partial pressure of particular gas in a gaseous mixture is directly proportional to the number of moles. Now another relation says that Pi is proportional to Vi, that is partial pressure of a particular gas in gaseous mixture is directly proportional to the partial or reduced volume of that gas. So in terms of masses, the identities 1 and 2 gave us this relation, that is Pi upon P is equal to Mi upon M into Ri upon R. So for gas A, Pa upon P is equal to Ma upon M multiplied by Ra upon R, and so on. For all the gases, you can write down this equation. So a general equation for any gas component, Pi is equal to P into Xi Ri R. That is, the partial pressure of any gas component is equal to the mixture pressure multiplied by the mass fraction multiplied by the gas constant of that particular gas divided by the gas constant of the mixture. So remember this equation, which will be used frequently. Now with the help of the thermodynamic relations that you studied till now, you can find out for a gas mixture, gas constant, its molecular mass and specific heats Cp and Cv. Let us take up gas constant. For each constituent gas mixture contained in the vessel of volume V and temperature T, we can write PAV is equal to MARAT. This you have already seen. So similarly for component B, PBV is equal to MBRBT and so on. Right. Now adding these equations, you get PA plus PB plus PC multiplied by total volume V is equal to MARA plus MBRB plus MCRC into T. So according to Dalton's law, the sum of partial pressures of constituent gas gives the total pressure exerted by the mixture. So replace this PA plus PB plus PC with the mixture pressure P. So PV is equal to MARA plus MBRB plus MCRC multiplied by the temperature. Now for gas mixture, PV is equal to MRT. This can be written as PV is equal to, replace M with components, sum of the mass components, that is PV is equal to MA plus MB plus MC into R into T, that is MRT. Now compare these two identities. You can say that R is equal to MA upon M multiplied by RA, MB upon M RB, MC upon M RC, where MA upon M is mass fraction. You can write it as XA. Similarly for this, XB, and for MC upon M, XC, and so on. So the gas constant R for mixture will be given by XaRa plus XbRb plus XcRc and so on. For any gas, MiRi is equal to R0, that is universal gas constant, is given by the molecular mass multiplied by the characteristic gas constant of that gas. From this, you can write the same equation in terms of molecular mass and universal gas constant like this. I hope you understand it. So this can be written in general form like this: R is equal to R0 into Xi upon Mi, where Xi is indicating the mass fraction, Mi molecular mass of component I, R0 universal gas constant, and R is the gas constant or characteristic gas constant for mixture. Now in the similar way, you can find out the molecular mass from the equation that you saw just now in the last slide. You can say that R mole or R0 upon molecular mass is equal to Xa R0 upon Ma multiplied by Xb into R0 upon Mb plus Xc into R0 upon Mc and so on. Or this gives you 1 upon M is equal to Xa upon Ma, Xb upon Mb, Xc upon Mc, where this capital M indicates the molecular mass for mixture. Ma, Mb, M and Mc are molecular masses of for gas components A, B and C. Just reverse it so that you get the expression for molecular mass M, right? So this is how you find out molecular mass and gas constant. Now this is in terms of mass fractions and molecular masses of constituent gases. You can find out in terms of mole fractions and molecular mass also. From this equation, that is M is equal to Ma plus Mb plus Mc, you can replace mass by number of moles multiplied by the molecular mass of mixture Nm, and for component A, NaMa, NbMb, NcMa, NcMc, this is Mc, right? So M, that is molecular mass of the mixture, will be equal to Na upon M, Ma, Nb upon N, Mb, Nc upon N, Mc, that is YaMa plus YbMb plus YcMc, right? Mole fraction multiplied by the molecular mass. So this is how you find out the molecular mass in two different ways, in terms of mass fraction and molecular mass, and in terms of mole fraction and molecular mass. Both can be used while solving numericals. Now this is another law, that is Gibbs-Dalton law. It states that the internal energy, enthalpy and entropy of a gaseous mixture are respectively equal to the sums of internal energies, enthalpies and entropies which each component of the gas mixture would have if each alone occupied the volume of the mixture at the temperature of the mixture, right? That means internal energy U of mixture is equal to UA plus UB plus UC. Similarly, enthalpy capital H is equal to HA plus HB plus HC. Entropy S is equal to SA plus SB plus SC, right? Now with the help of this, you can find out specific heat also. First of all, let us take the internal energy equation. U is equal to UA plus UB plus UC. Now if you have specific internal energy U for mixture, that is lowercase u, and M is the mass of the mixture, then M into U indicates the total internal energy, capital U, right? Similarly, MAUA indicates the total internal energy, where UA is the specific internal energy, MA is the mass of component A. So this equation we have obtained as per Gibbs-Dalton's law. Now M into U is internal energy, that is given by CVDT. So Mu is equal to MCVDT. Similarly, if CVA is the specific heat at constant volume for component A, CVB is the specific heat of component B at constant volume. Similarly, CVC is specific heat at constant volume for component C. Then you can replace MAUA by MA into CVA dt, MB CV dt, MC CVC dt. Right? Now from this you can find out CV by dividing the right hand side by M dt. So this becomes CV is equal to MA upon M CVA, MB upon M CVB, MC upon M CVC. What is MA upon M? Mass fraction XA. So XA CVA plus XB CVB plus XC CVC is equal to CV for the mixture. Right? I hope it is clear. In the similar manner, you can find out first enthalpy equation and then specific heat at constant pressure. Now, as per Gibbs-Dalton's law, capital H is equal to HA plus HB plus HC. If lowercase h is the specific enthalpy of the mixture and HA, HB and HC are corresponding specific enthalpies for component A, B and C, then you can, from this Gibbs-Dalton's law, you can write that MH is equal to MAHA plus MBHB plus MCHC. Now replace MH by MCP delta T. This you have already studied, that enthalpy can be written in terms of Cp and dt. Similarly, MAHA will be equal to MACP delta T, MBHB is equal to MBCP delta T, and so on. Divide by MCP, you will get this equation, where MA upon M is mass fraction again, can be replaced by XA, MB upon M mass fraction for component B, replaced by XB, and so on. So this is the equation for specific heat at constant pressure of mixture. Right? Now finally we can find out entropy for the gas mixture using Gibbs-Dalton's law, which states that capital S is equal to SA plus SB plus SC, that is, sum of the entropies of different components is equal to the entropy for the mixture. Now if you write the equation in terms of specific entropies, then MS, that where S is the specific entropy of the mixture and M is the mass of the mixture, is equal to MASA plus MBSB plus MCSC, where SA, SB and SC are specific entropies of components A, B and C. Divide by M, you will get this equation, which can be written in terms of mass fraction like this: XASA plus XBSB plus XCXC. Right? Now DS will be equal to, from this equation, XA DSA plus XB DSB plus XC DSC, where DSA, DSB, DSC can be calculated from TDS relation. TDS relation you have already studied in first year. TDS is equal to DH minus VDP. DS can be replaced by CPDT. So CPDT minus VDP, just divide by T. So DS is equal to Cp dt upon T minus V upon T dP. V by T can be replaced by R by P. So this is equal to Cp dt upon T minus R dP upon P. Now if you integrate it from state 1 to state 2, that gives you ds is equal to Cp ln T2 upon T1 minus R ln P2 upon P1, 1 to 2. For ith component, this can be written in generalized form like this, right? I hope it is clear. So with this, we finished part 2 of the chapter mixture of gases. I hope you have understood everything. Now we'll solve some numericals and then proceed further in the next class. Good luck.